All right, so as you can see on the handout, we've got 3 that we're going to do today, 3 that we're going to do tomorrow. So those are all the ones that we're going to go through. There's a number of different types of these, but there are some tips or strategies or whatever that are going to be similar for sort of your similar goal or similar approach for all the different types. Okay, but they are very specific, I would say. So here are some of the things that you want to think about. Drawing a diagram if possible. I think most of them you can draw a diagram. Some of them, if you're not good at drawing, that you might have a hard time with it, but you can give it a shot. Define any other variables. If you put a variable on a diagram, that counts as defining it. So if you draw a diagram, then you may not have to, but if you don't do a diagram, then you have to absolutely define any variables that you use. Define the domain of the variables. Now, again, this is going to work better in some cases than in others, and it's not that it's necessarily required, although I think you should try to do it, and I think you should do it, and it's going to help. But for our solution to be complete, you'll see when we get there, but there'll be a place where we're going to use the domain if we've stated it. So that is something to think about. State what is being maximized or minimized. Again, this isn't a requirement per se, but it is, I think, a really good tip because it forces you to do the next step, which is write an equation, and we're going to eventually get it into one variable for that thing that you're maximizing or minimizing. So some questions are going to talk about multiple things. They might talk about volume and surface area, but only one of them is being maximized or minimized or whatever it is. So you need to make sure that you're writing the right formula that you're going to end up using to solve the question, okay? And it kind of is going to, I think, give you a target. If you say maximize area, then you have to come up with an equation for the area. You know what I mean? Okay, so then you write the equation, and you may need to substitute so that it ends up being in one variable. We'll see examples of that as we go. Then obviously, this is calculus. You're going to take the derivative. Some of these questions are very similar to grade 10 questions, and some of them will be quadratic, so you could solve them the grade 10 way. But this is calculus class, so you need to use calculus. If you try to do it a different way, you're not getting marks on a test for that, obviously, right? So we take the derivative and determine where it's equal to 0 and where it does not exist, and then sort of analyze the critical values to determine which one is the solution that we're looking for. I suppose it's possible that you could have questions that have multiple solutions. The ones that we're going to look at don't, but it's not like it's impossible. But generally speaking, that part's going to be relatively straightforward, I think, if you've done all the rest of the steps correctly. But again, it's not something we've talked about, that you always end up interpreting and analyzing your result to determine what the actual solution to the question is, right? And then answer the question. And in some cases, we might do a check. In all cases, we'll think about whether our answer makes sense, and if there's anything about the question or about the algebra that we've done that might help us kind of check our solution, I suppose. Okay, so those are the tips. And as we've talked about before, when you go to practice these yourself, you might want to go and review those tips just to get on the right track and say, okay, these are the things, these are the little things that I can do that are going to help me keep me moving in the right direction. All right, so we're going to do the first 3 from day 1. Let's get started. This is one that you might recognize from grade 10. Farmer has 1,600 meters of fencing with which to create 3 identical rectangular fields. If one side of each field needs no fencing because it adjoins a river, find the dimensions of the field that will maximize the area. So this is one of the types of questions, and it could change a little bit if there were 4 identical rectangular fields, or if it changed the amount of fencing that you have. But again, generally, the approach is going to be the same, just the numbers might be a little bit different, right? All right, so I think I'm paused here.
Hello, Mr. There.
Hi.
Do you have a new student?
All right, here we go. So first thing we're going to do is we're going to draw this one. This one is definitely one that we can draw. So there's my water. Here's my full area, and I'm going to split it up into at least roughly, that's not bad, 3 identical rectangular fields. Now I'm going to come up with some variables. Where you put the variables, I mean, if you do it the same way every time, you're not going to practice this specific question that many times. But if you kind of try to do it the same way every time, then again, the algebra might be a little bit more familiar. But you know, you don't have to do it one way or another way. You can do anything. But I'm going to put x on this side, and I'm going to make y this entire length. What else can I do? What else can I add to this diagram that's going to maybe help? Anybody have an idea? If this side length is x, all of these are x. And those are all fencing, so I need fencing for all of those. Okay, we are maximizing area. That means eventually I'm going to come up with some kind of equation for the area, right? And then we're going to maximize it by taking the derivative and finding the critical values. What would the domain be? We're just going to do a domain for x here. What would the domain be of x? In other words, what are the possible values for x given the circumstances of this question? And the fact that we're in the real world.
X is a real number between 0 and the length of the fencing the farmer has.
Okay, so it's a real number. Well, we're not going to do it formally, so we don't need to include that part, but that's very good. So it's definitely a real number, and it's definitely a positive number. We all agree with that because it's a length. Okay, so it's going to be greater than 0. Is it less than 1600 or? What is it less than?
Could it be less than y?
I mean, yeah, it could be less than y. That's not going to help us because we don't know what y is.
It's less than a fourth of the total fencing?
Yeah, good. So 400, right? So it's going to be less than 400 because we're going to have 4 of them. So if they added up to 1600, y would end up being 0. So it's not less than or equal to 400. It's strictly less than 400. Everybody got that? It's not, it can't be negative because it's a length. And it's going to be less than 400 because if it was 400, then that would be all of the fencing. You wouldn't have a fence the other direction. You'd have 4 fences sitting on top of each other or something. Okay? And if you wanted to do this for y, then it would be 1600. But we're going to, and so it's fine to do it for both. In the end, I don't think we're going to need the one for y. But you could think of it that way. And it's the same idea, except we only have one y, so y could take up almost all of the 1600. You don't have to divide it by 4. I've seen some people do this question where they let y equal just one of the sides. Okay? And there are sort of pros and cons to both. If you want to try doing it that way, you can. Your setup's going to be slightly different, but I bet you could kind of figure that part out. And it's not going to really make the question easier or harder. All right, so we've got our diagram, John. We've got our what we're maximizing, defined our domain. Area is length times width, which is y times x, or x times y. We need an equation in one variable. So what do we do? Like, this is stuff you've done before. This is the kind of thinking that you've done in other kinds of questions. David?
The derivative with respect to one of the variables.
But we're gonna write it with only one variable first, and then that's what we're gonna do, absolutely. Otherwise, it would be, it would be a lot more complicated. You're on the right track.
Would be y times 1600 minus y.
Yeah, but I'm going to do it the other way. 1600 minus 4x. And there's your substitution. You'll notice often when we do this, we rewrite this, we use function notation, but you can only do that when you've got it in one variable. What do we want to do now? Huh? If we took the derivative now, it would be product rule.
Expand it.
Yeah, I think it's easier to expand, don't you? This goes back to, whoops, all that time we spent thinking about the right way of, or the most efficient way, maybe not right way, but most efficient way of doing these. All right, A prime. And I factor this. That's not always going to be factorable. It's not necessarily worth factoring. I'll show you what I mean by that later. We'll look at an example where we can do these in different ways. And that's going to come down to what you're comfortable with or what you notice. Okay, now for critical values, A prime equals 0 or does not exist. What's something that we know about A prime?
It exists at all x values.
Very nice. It's a polynomial, so it exists everywhere. And this is what I've been saying since the beginning of the unit, that also in these word problems, you need to make this statement every single time. Sometimes it will have places that it does not exist, so that you don't just always say it exactly the same. But if it exists everywhere, you got to state that, okay? And where is it equal to 0?
When x is 200.
Good. So we only have one solution, so that had better be the solution. This one's easy to check, so I'm going to check it. If I do A prime, this is almost like a first derivative chart, but I'm not writing out the whole thing. So if I put 199 in, I get 2 negatives, so it's positive. Then it's 0. Then when I put 201 in, I get 1 negative, so it's negative. And I like this check when it works. It's only going to work really if we are able to factor it. Otherwise, you could use your calculator, like you could do that. I just like it because it's familiar, because it's the stuff that we've been doing, kind of like the table. And we don't have to do a whole formal table. We're not doing a sketch, not classifying things. So it's a bit different for that, but right? We got positive, then 0, then negative. We were supposed to be maximizing, and we maximized. The questions are designed such that you will find the maximum if it's a maximum question and you've done it correctly. It's not going to find you a minimum, or there'll be some other reason to discount the minimum if it has one. So you don't have to really worry, like, you don't have to force the question to be a maximum. It will be a maximum. If we go up to the original, it's a quadratic with a negative leading coefficient. So like, it's going to have a maximum. We can see that from the beginning. That's another piece of evidence you can look for. If you write this out and it's a parabola that opens up, well, you've done something wrong, because that one doesn't have a maximum, right? But that only works in certain cases. That's not always going to work. Okay, so now we've got our x. Our y is 1600 minus 4x's. So 800. If the question said find the dimensions of the 3 identical fields, like, then you'd have to answer that question. And if that was the question, then maybe you define y to be that. So when you solve for y, you get, but like, that's kind of up to you, okay? And obviously, if you did it that way, that's going to change this, because you'd have 3 y's. So it'd end up being over 3, which is awkward. But you could do it, it'd be fine. Okay. This one doesn't really clarify, it doesn't really specify, so we're just going to take it to mean of the whole field and make that statement. What do you think? Is that okay? All right, let's move on to the next question. So we're taking a square piece of cardboard, cutting a corner of equal size, or cutting an equal amount out of every corner, and then we fold up the sides to make a box. So we're making a box with an open top from a square piece of cardboard. So what exactly does that mean? Oop. Let's see if we can draw a square. Bad. So picture this. Cut off a corner, cut off a corner, cut off a corner, cut off a corner, and then these flaps fold up to become the sides, and as long as the dashed lines are of equal length, they'll all kind of match. You know what I mean? You could try this if you wanted to, like with a piece of paper. Later, if you have time. Okay? Okay. So how do we solve this one? Let's start labeling this thing. Box with an open top is to be made from a square piece of cardboard, side lengths 100 centimeters. So that's 100. That's 100. What do we do? Very nice. So, and I'm not sure if this is exactly what you meant, but I hope it is. We're going to make this x the variable. So we're not going to make it this. We're going to make it the size of the slits. And they're all going to be equal, so it's going to be on every one of these. You don't really have to write it on every one, but... I'm going to attempt to draw this again, but looking like a box, and I think that's going to help us understand where things are going. You don't have to do this. If you've done it once and you're good at visualizing and you can write the equation, then go ahead and do that. But if you want to visualize exactly how this works, whoops, didn't mean to erase those. So that's like the back of the inside of the box. It's a little wobbly, it's only made of cardboard. So we're trying to maximize volume. Folks, this is another type of question that we're looking at. So, there's going to be one like this in the homework, and you will have already done one like this. But I also like walking you through how could you approach this problem on your own? And that would be challenging, I fully admit. But pay attention to the strategies, the little things, and try to remember them for later in your life when you actually have to do real problem solving. So we're maximizing volume. We are not yet ready to define the domain of x, I don't think. What is the formula for volume? Very good. So I need length and width and height written out in terms of x. Can we take this and use it to label that so we know what the length, the width, and the height are? Like, can you visualize where the sides of this box come from, given the first diagram that we drew? Who can help? Anybody? The height is x. Very good. And?
The length and the width are both 100 minus 2x.
Very nice. So this length here, see, we could have talked about this before, but the strategy here is, and it's similar to what we talked about when we did related rates, and we said, well, when you take the derivative and you look at what variables are in there, you may have to go find some of them. Length times width times height, we need to find them. Oh, I need to find out what this is. Well, it's this length here, right? Like, I know that, so now I know I need to come up with an expression for that, and it's 100 minus 2x. Take an x from one side, x from the other side, 100 minus 2x. So what is the domain of, yep?
Sorry, so I understand the 100 minus 2x, but why would the height be x? Like, wouldn't there still be pieces missing?
So imagine folding the flap up. That's your height, which is this side length, which is the x.
So there's nothing missing.
No. The lower bound for these is usually easy. What's the lower bound? What was it in the first question?
0.
Yeah, 0 again. Is there an upper bound? Close, not quite. 50 because you got x on both sides. So if I take 50 off one side and 50 off the other side, then the other dimensions are 0, right? So the fact that the other dimensions can't be 0 gives me an upper bound for this, but we will see examples where there is no upper bound, okay? All right, so now I can make my function here. So I've got 100 minus 2x times 100 minus 2x, or 100 minus 2x squared times x. So I'm going to expand all this. Negative 2x times negative 2x is 4x squared times x is 4x cubed. You're not always going to try to do this in one step, but to save us some time, I think we can do that. Negative 200x minus 200x is negative 400x, but times x is negative 400x squared. And 100 times 100 is 10,000, so plus 10,000x. If I left it as 100 minus 2x all squared times x and did product rule, I mean, it would work. It wouldn't be that hard. That's a pretty easy product rule. But again, I think it's worth your time with these polynomial ones expanding, because their derivative is going to be a lot easier. Okay, sometimes for these we don't, like if it's factorable and it's easy to factor and you do b squared minus 4ac and you see that it's factorable and you factor, or the other one was just like a common factor, right? So that was an easy one to factor. Then sure, go ahead. But sometimes what we do for these ones instead is we go for critical value b prime at x equals 0 or does not exist. Once again, whoops, not c, v prime exists for all x because it's polynomial. Whoops, I meant to do this. When 12x squared minus 800x plus 10,000 equals 0. You just set it equal to 0 and solve it like a separate equation. So it's kind of up to you, your preference. We can divide 4. We can divide both sides of the equation by 4. Four is gone because I can divide it out on the other side. That's equal to 0. B squared minus 4ac. Audrey? 10,000. That's what I got too. So it is actually factorable. But I don't know that I want to factor that, so I think I'm going to use the quadratic formula anyway. So that's 300 divided by 6, which is 50. And this is 100 divided by 6, which is 50 over 3, which is about 16.7. So what now? Jasper?
We figure out which one's a max.
So how?
Check it.
Okay, so you could do that. You could do the whole chart, or you could just kind of do an informal check or something.
The domain we have,
So can you elaborate?
the x is 50, it can't be 60 or bigger.
Yeah, so that's a minimum. That's when you would have a side length of 0, right? And you're gonna have a minimum because you will have no volume. So this is outside our domain. But you can only state that if you've stated your domain. Do you understand? So you can't just all of a sudden pick one and say it's outside domain. If you get a negative, we've always let you say it's inadmissible because you can't have a negative length. So that, I suppose, would be fine. The problem is often with these questions, you don't get a negative. You get 2 positive answers, but one of them's outside the domain. And, just barely. It's at the exact point where the domain ends. So if you state the domain, then you can say that. Otherwise, I think you're doing a check either into the volume to see what volume it gives you. And you would find this one gives you a volume of 0. And the other one gives you a volume or something along those lines. But I would have to see that. So this is why it's in your best interest to try to work on the domain so that you have proof or evidence to make this statement at the end when you have 2 solutions, which one is the solution that we're looking for. Does that make sense? Kind of get that? Okay, so now we are going to figure out our dimensions because the question said, find the dimensions of the box of largest volume. So our height was x, so our height is 50 over 3. We're going to do these like as decimals, not as a fraction, because that doesn't really make a lot of sense in measurements like this. And the length and the width equal each other, and they're both equal to 100 minus 2 times 50 over 3, which works out to about 66.7. And we're talking centimeters here, I believe. Questions for that one? Yep.
How come you didn't do the check on that one?
Just chose not to because it's not necessarily required, and this one's not in factored form, so I can't do it by inspection. So it's up to you whether you want to do that in your calculator or not. If it's on a test and you have time, then yeah, absolutely you could go for it. It was factorable, so if we did factor it, then I probably would have. Any other questions? All right, last one. Another box. This one's got another layer to it, though, not the box physically, but like the question. Open top box. So that's going to be relevant because if it has a top or not, this is talking about surface area, so that's going to matter. Okay. An open top box with a square base, again, that's also going to be relevant, is to have a volume of 2,000 centimeters cubed. The box is going to be constructed of material that costs $5 per centimeter squared. I think that's the sides of the box, and the base of the box is $12 per centimeter square. That's missing sides in there. Find the dimensions of the box that will minimize the cost to make the box, and find the minimum cost. So there's a little bit extra at the end there, but factoring cost into this is also going to make a difference. Okay? Once again, let's draw it. So I'm going to call this x, which makes this x, because it's square, it's got a square bottom. I think that's better than making the height x. So we'll call the height h. We're minimizing cost. Does anybody know what the domain of this one is going to be? X has to be greater than 0 for sure, right? We know that part. Does it have an upper bound? What happens is x gets really, 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 really large in every direction.
Volume gets bigger.
The volume gets bigger unless the height gets smaller. If the height gets smaller to match the x growing, to keep the volume at 1,000, you'll eventually have a pretty short box. What do you think, Kate?
Yeah, I was gonna say like it just couldn't be 0 because then we wouldn't have a volume.
Yeah, yep.
With the square root of 2,000.
I think that it's just x has to be greater than 0. I think there is no upper bound because you can always make the height smaller. The height could get infinitely small. The reason why the other two were is because there was boundaries based on the length because of the amount of fencing, and the size of the one side had to be 100. You know what I mean? So that's why they had an upper bound, but this one doesn't. It's just a lower bound. So x has to be greater than 0. Okay. Here's the hard part. I'm just going to do this part for us. We're talking about surface area here because we're talking about the sides of the box and the bottom of the box, and that's surface area. And again, it's an open top box, so the top, there is no top. Okay. We need to have this in one variable, so I need to use volume, length times width times height. The volume is 2,000. X squared times height. So again, going back to the domain, the height can't be 0, but it never will be. X is going to get really, 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 really large. That won't make the height 0, right? So we're only worried about the domain of x. We would have h has to be greater than 0 as well, but that's not going to be in our equation, so we don't need that. But if that helps you to kind of think it through, then that's fine. But h won't be 0, so x can be as big as it wants to get. And it's going to make h really small, but it'll always mathematically work. Okay, here's the next part. Here's what makes this one a little bit tricky. And you might just want to watch and then you can copy it down after. Surface area. We've got the bottom of the box, which is x times x, so x squared. And what about the sides of the box? Yep.
4x8.
Very good. There's 4 sides. They're all the same because it's a square base. So for that, I would add 4xh. And then we can sub in for x. But that's not the question. The question is minimize cost. And didn't I say to minimize cost, you got to have an equation that says cost equals? So this isn't the equation that we want. How do we turn this into an equation for cost? If this is the base of the box, and that's going to be like the centimeters squared of the base of the box, because x times x will give me centimeters squared, then isn't this 12x squared? And the sides cost $5 per centimeter square. So the sides are $5 times the area of the sides, which would be in centimeters squared. Now we need to write this in terms of one variable. Could have done the same over here. Whoops. So here's the thing. Some of you are just going to want to go straight to cost because you're good at visualizing and you understand and you can figure out what the bottom is and what the sides are and kind of do that part and then just add the cost of the sides out front of it. Some people might want to do those things one at a time and do a separate example of surface area. But you got to make sure you know that that's not the one that you're solving because that's not what we're minimizing. And that's why writing out what you're maximizing or minimizing can be useful to make sure that you get the right equation. Okay? So you kind of have options there. Does that make sense? And you can sub in for h here or you can sub in for h there. That part doesn't matter either. But now we've got our equation in terms of one variable. I'm going to clean it up a little bit before we take the derivative. And that was why I kind of skipped the part of, and I just did the volume because I wanted to chat about that. And I wanted to have the height. But if you might have done this part first, realize you have height, and then realize that's why you're given the volume. You're given the volume so that you can find the height, right, in terms of x. So 20 times 2,000 is 40,000. And x over x squared just means it's over x. Or x to the negative 1. Right, because that's how we're going to take the derivative of this. Minus 40,000 over x squared. Everybody good? I'm going to go ahead and get a common denominator. So this one's rational, so it's got a place where it doesn't exist. At x equals 0. What about that? Yeah. Outside our domain again, right? This has got to be greater than 0. Move the 40,000 over, divide by 4. 24, sorry. 4. I don't know why I said 4. Then cube root, very good. We could have simplified that fraction. If you want to let your calculator do that so it's a bit easier to write, go for it. Put this in the calculator, and I get 11.9. If somebody wants to confirm that, that'd be great. Once again, we were supposed to find the dimensions of the box and the minimum cost. So the dimensions of the box are the width and the length are equal because it's square base, and that's our x. And the height was 2,000, yep, over x squared. Now when I put this in, I'm using the exact value of that, right? How do we find cost? Yep.
We use the original cost equation, so 12x squared plus 5 times 4x.
Yeah, or one of the simplified versions or whatever. Like, but yeah, you're right. We've got an equation for cost. Let's use it. Like, don't go back and rebuild it or think it through like that or anything. Use your equation for cost. So C at 11.9. Again, I'm going to use the cube root of 400,000 over 24 equals 12. So let's see, cube root inside, try that again, cube root divided by 24. Okay, and then it is 12 times the answer squared plus 40,000 divided by answer. Therefore, centimeters, I think, yeah. Any questions? Any questions? So those are the 3 types. tomorrow. Oh, I don't have that in front of me. Here they are. There's two more types. We're doing two examples of one that's similar. There's a slight change between them, but it's the same kind of idea. So, and the other one is actually not really different from these ones either. Any questions?